Hey, hi Mukesh. Are you able to hear me?
Yes, sir, I can hear you.
Yeah, so let's wait for a few more minutes.
Yeah, sure.
Okay. Good evening, Mukesh, Himanshu, and Aditya. Okay, let's get started. Yeah, Mukesh, you can go ahead.
I understood the concept of CNN. Okay, now I need some, you can say the practice, which I written in the WhatsApp chat also. Okay, that how to use it so that we can able to test it. What Professor Sir has teach us. Okay, like we have the image parameters, then we are reverting back to the original images. So that way we can, if something is possible, then it will be more learning experience. Okay. Theory part almost I understood. Okay, the way the scenes are working.
Okay, so you want to see kind of how we apply CNN for various tasks, and also how do we visualize kernels?
Yeah, right.
All
Because
this.
in in MLP we use this ImageNet dataset, and from there we are figuring out like one, two, and that part we have done using the normal, you can say scikit-learn packages. Okay.
You mean ImageNet or MNIST?
Sorry, image not
Okay,
image.
okay, fine. Okay, that's your wish. So you want to see the code.
Yeah, something even in internet. Or also the problem is that I know how to use the TensorFlow, but I never work on PyTorch. Okay. And I understood that the PyTorch is better than TensorFlow because PyTorch is giving some open thing, means they given some function which you can able to change it. You can able to overwrite in internet. So some kind of help you can give internet PDF file or something, or if possible, can you just show how to start it in the collab? Then we can able to, at least I can able to grab it.
Yeah, sure. Okay, so I actually, uh, you know, so I'm taking a collab where in one of the workshop I used CNN just to demonstrate how we can use CNN for classification task and transfer learning and all those steps. So I make use of the same collab now.
Mhm.
Yeah, so before moving on to that, I would like to hear from
Yeah,
Himanshu
please.
and as well as Aditya. Yeah, Himanshu, you can go ahead and what do you want to discuss in this session?
Okay, so I have like around 7 or 8 questions, mostly theory related to week 9.
Week
Uh,
9, what's the content by the way? So it's that vectorial representation of words.
yeah, that hierarchical. Uh,
So you want me to
so the
share
names
the
are
slide?
hierarchical, softmax, and all.
Okay. So you want to discuss on
Like I will ask the questions if need be. Sir, before
yeah, please go ahead.
yeah. So before that, for other subjects, the deadline for week 10 is 13th. So
Okay.
what will the deadline be for DL? Because till now, even the videos are not up.
Okay. So I was just thinking because we have shifted, the deadline for week 7 or week 8 by a week. So this has a repercussion for the rest of the week. So it will be a deadline. I mean, the deadline might be 16th of Wednesday for week 10.
Okay.
So it's kind of we are releasing the content on every Wednesday and then giving you a week time to submit the assignments.
Okay. Also, sir, quickly, can you comment on that thread on Discourse yesterday about transfer learning?
Yeah, sure. I will discuss that. Yeah, I think it's first I discuss
Yeah.
the coding part for. How do we use CNN for classification task? Then I discuss about this transfer learning. Yeah, I've gone
Okay,
through
sir.
that thread. You have answered most of the questions, and I
No, no.
don't have it. Yeah.
I just wanted to confirm that I have not written anything wrong. Like
Okay,
because
fine.
I'm new to this. So, but this was like my meta questions, so not the that important. So coming to lecture 1, can you tell what cosine similarity is and how to calculate that mathematically? And also, what is the physical importance? Does if 2 points are cosine similar, then does that mean that they lie beside each other on the graph, something like that?
Okay, I will address that. Yeah, Aditya, what do you want to discuss in this session? So I just want to see whether are there any overlapping content so that I can discuss in general.
So I have just a minor doubt. I will ask you later. So
Okay.
please carry on.
Okay. Then I first talk about the coding aspect. By the way, I can't talk in detail. I just show you the overview on the important functionalities and the modules in PyTorch.
Yeah, that's enough. Yeah.
Yeah. So let me share the screen. Okay, so you are able to see the screen, right?
Yeah, right.
Okay, the collab. So are you able to read it, or do I need to zoom in a bit?
It is good.
Little bit.
Okay.
Yeah, it's enough. Yeah, enough.
Okay. Yeah. So we rely on a single package, Torch. So that's how we import PyTorch into Colab. So you can also install PyTorch in your local system, but that's a different story. Of course, Colab has these feature. Either you can run your algorithm on CPU or GPU. So I have chosen GPU. So you can actually choose that whether you want to use CPU or GPU. So once you choose your machine, then you can check whether. So this is just a setup. Okay, so it's nothing beyond that. You are just checking whether GPU is available or not. So PyTorch can run both on CPU as well as GPU. So that's a difference between this NumPy package and then this deep learning framework package. So both deals with tensors, but the deep learning frameworks can run on GPU. So that is the core difference. So why don't we make use of the GPU? So we are just checking all this. So you can see the properties, all these. We are using Tesla T4 GPU, all the available memory, all these things. And for some reasons, I'm just choosing a data type as torch.float and also device as CUDA. So if you have multiple GPUs, you can control how many GPUs you want to use, or in which GPU you want to, or if you want to parallelize your computation, you can do that here by configuring this device functionality. And then for computer vision, of course, CNN is most commonly used for vision tasks, especially for image classification or video, something like that. So it's a 2D CNN is used for image, and of course, you can use 1D CNN for speech or whatever. So now we are going to, or I am going to just demonstrate it for classification, image classification task. So we are just using this torch vision, which contains many useful functionalities for vision task. And of course, from torch vision, we are doing these transforms and importing these transforms. So you might have guessed transforms are used to do this data augmentation, right? So we can rotate the image, scale it, or do some shear transform. All these things are available in this functionality. And this is most commonly used functionality, that is data loader, which help you to load the data. Okay, be it if you are using benchmark datasets, you can directly load it, or if you are using your custom datasets, you can follow some structures. You keep your data in a particular structure and then make use of this functionality to load those data. So this is a most commonly used one. Not most commonly, it has to be used. Okay, and this, of course, So if you want to see what are all the data sets are available for vision related tasks, you can simply print and see there are so many data sets. Okay, it's not just MNIST. Even you have this image in it here. So when you say vision, it means not just classification. It means object detection is also belongs to vision. Face recognition. Okay, so there are a wide variety of vision tasks. So you can use any, the suitable data set for your vision task. So here we just want to use a simple data set that we call CIFOR10, which contains 10 classes. And also we have another big data set, comparatively big, that is CIFOR100, which has 100 classes. So Yeah, anyhow, we do some sort of augmentations just again for the demonstration purpose. It is not necessary that you have to use augmentation, but when you have, very less samples, or if you want to, of course, from the regularization perspective as well, you can do these data transformations. And then for that, we use this transforms functionality, and you can add more. So I am doing only 2 transformation here. Of course, this is just a conversion, not transformation. And then we do some normalization. If you want to add rotation, you can add it here. So which means this particular transformation will be applied on each and every image or every samples in the dataset. And I'm just downloading the dataset. So since these are all benchmarks dataset, you can directly load it from the torch. So I forgot to execute. Let me execute this. Yeah, so the useful thing, once the structure is always same. First, we load the data, we understand the data. So whatever that related to this data, we do this in the first. This is the first step in machine learning. Then we create the model, then we train it. So we follow the same structure here. Yeah, so then you can see what are all the classes and the data shape, all this. I think I didn't. I'm just downloading it. So there are 10 classes, as you can see from here, and 50,000 images, which is in training set. And so this is a tensor. So everything is downloaded as a tensor. So 50,000 denotes we have 50,000 samples, and 32 and by 32. So the image size, the spatial dimension is 32 by 32. Then it has 3 channels. Okay, so it's a very simple block. So you can think of like that. This is an input to the convolution layer. Okay. Of course, once we have this training set, then if you want to do this batch training, we can. The data loader has a lot of arguments where you can control many things. So one thing that we often do is we fix the batch size. So I am just, again, for quick demonstration, I am setting it as 4, and then you can decide whether you want to shuffle the data samples in the data set or this. Nothing big. Yeah, I'm just giving.
This loader will what? This loader will data loader will do. It will train the data set, or it will just shuffle it.
No, so data loader is actually a Python generator. Okay, so it is not creating any new memory. So it's a generator. So whenever you call it, okay, so it will return 4 samples, and then those 4 samples are actually taken. So if you give shuffle is equal to true, then it will shuffle the data set every time, and it randomly pick those 4 samples from the data set.
Okay.
So you can see, of course, when you see once the data set gets loaded, right? So you can see how much memory it actually takes. So most of the PyTorch functionalities are like it's it won't copy everything in. If you create a dummy variable or another variable, if you assign it to that variable, it won't make any new copy. So it takes a view. So it's a so efficient usage of memory. Yeah, you can, but the important thing is it is a generator function. That is the only thing that you have to remember. So whatever that related to this generator function, you can manipulate it. It's of course. So since it's a generator, so how do you get a sample from a generator? So you have to use this. I am using this explicitly just to show you that we can take 4 samples at a time and see. I want to see display some of the samples in the data set, and just to cross check whether the labels are correct, or are there any errors in the labels. So that I want to explore. So I'm just taking, I'm just taking 4 samples and just plotting it and checking. So every time I call this next method, it will randomly take 4 samples. Of course, since it is 32 by 32, it's very small. Of course, I hope it's very difficult to recognize this is a cat unless I put this label here, and extremely difficult to recognize this is a frog unless we have a label here, because it's a very small image, color image. Of course, you can run it next, you will get a different samples. Every time you run, you will get a different sample.
Okay, understood.
And we can see that the labels are proper. And once now we have the data, so the next step is to construct the network. So the easiest way of doing is by using this NN module. Okay, so torch.nn is the core engine to build any neural network, be it ConNet or whatever, simple neural net or RNN, whatever. So if you want to build a neural network, then this torch.nn module has all the necessary functionalities like optimizer or whatever. So any different type, we have different types of layers like fully connected layer, convolution layer, and then word embedding. So almost all of them are there in this torch.nn. And it also has, of course, I don't want to elaborate on this functional. So it has also something called as functional. You can, both of them have the same functionality, but they differ in their way of usage. But just for the time being, you just make a note of it. We have torch.nn module, which is core. And then we have to use that in order to build any neural network. And here to build CNN, so this is a base class. NNN is torch.nn is a base class. Then we simply make use of it and create a subclass of it, and you can give any name to it. And here so when you call this init, I hope you know what happens actually when you take a when you create a subclass using a base class, then you should know what happens when I call this again.
We internally call the base class.
Yeah, so there are many things happening behind the screen. So the only way to figure out what is going on is to look into this base class. So once you look into the base class, then you know how to make use of that, and you know how to create an efficient or effective architecture. So we define all these steps. Okay, so we build the convolution layer here, the architecture here. You can see I'm calling this con 2D because we have con 1D, 2D, and as well as 3D. From this NN module, then we are passing some arguments. So this 3, so you can see is in channels. So my input channel, since it is a color image, it has 3 channels. So we put 3 here. So if it is a gray, we put 1 there. If we have some images, say from satellites, it might have 7 channels. Okay. Of course, based on the type of nature of images, we have different channels. And then I'm defining out channels. Okay, so which means what should be the output depth. Okay, so that is 6. And then the kernel size is 5, which is square 5 by 5. So we know that once we put this, of course, you can do, there are many other parameters. You can set stride, what is the stride value? So by default, it is 1. And you can also set padding, whether you want to do 0 padding. And dilation is something that usually when you do a pooling, it shrinks the shape. The dilation actually make it bigger. Okay, instead of shrinking, it expands. Okay, so if I have 5 by 5 and then if I use dilate, then I may get 8 by 8 or 10 by 10. So sometimes it is also called as upsampling, and there are some other useful arguments here. But for the time being, we are using only these 3. Yeah, so after this, I am using this pooling layer. So we have, again, this is just the size of this pooling layer 2. And then, since the depth, now the input depth will be 6 because we have 6 feature maps. And then I want to create a convolution layer 2 that has 16 feature maps. So 16. Again, I want to use kernel of size 5 by 5. Then after these 2 convolution layers, we create a linear layer. So note that I am creating a linear part of, usually we have fully connected layer where each neuron is a contains both linear part and as well as non-linear activation function. We are just building the linear part here. Okay, so we flatten it. By the way, we first flatten the convolution layer, which has height, width, and depth, and then we flatten it. We know how to flatten, and then we are manually putting all these values. You can automate that as well, but again, to understand how everything fits into this class, I'm just putting all these numbers explicitly. And then I'm just defining there must be 120 neurons in the first layer, and then 84 neurons in the second layer, and then 10 neurons because we have only 10 classes. The third layer.
Here, what is the size of the kernel? Will be 6 cross 6, and we have number of kernel is 5, right? And depth
Which
is
one?
3.
So you're asking about this one?
No. First one, that
This one.
convolution 2D. The first one, 1.
3. Yeah, this one.
Is the depth, and what is my kernel is going to be 6 cross 6, and number of kernel size is 5.
No. It's first is input channels. That is, what is the depth of my input channel? First number. So it's 3. And what is the depth of output channel? It is 6. So meaning that you have to use 6 kernels.
Okay.
So how many? You can think of how many kernels you want to use, whether 1 or 2 or 3 or 6. So I am just entering 6. So you after this convolution operation by each of these kernel, I will get 6 feature maps. So the depth of the output will be 6. And then the third argument is the size of the kernel, the spatial size, 5 by 5.
So what is the filter size here? It's a 5.
Yeah, that's 5 by 5.
5 by 5. Okay.
Yeah.
Okay.
Yeah, so they call, so I think in most of the framework, they call it as kernel. Yeah. Then you do this flattening. So now we have created this, the entire network. And then, of course, we have to do this nonlinear stuff. We introduce nonlinearity. So even in Con2D, so you can, I don't know what happens, whether I can share this screen. Are you able to see my whiteboard? I'm opening one.
Not yet.
Okay, so I think I can share it. Now?
Yeah, now. Yes.
Okay. So one way is that, so how this convolution layer differs from a linear layer or fully connected layer. So in general, we have this, we have a neuron is composed of 2 parts. So this is linear LI, and this one is non-linear sigma, say for example. Same thing is true for convolution layer. So we have this convolution layer. Okay, so after convolution operation, we have this feature map. Then we pass this feature map through this nonlinear activation function, where the nonlinearity is with respect to each element. So it's element-wise nonlinearity. If I switch it, which one you are seeing right now? The whiteboard or the collab?
Whiteboard.
Okay. I think I have to switch back and forth.
Yeah, now it's collab.
Yeah. So you might wonder, so why don't we, put all these steps into this initialization step? Okay, why are we using these separate steps? So I will discuss all these steps when we do this in the workshop. Okay.
Yeah. Okay.
For the time being, just accept all this, and then I'm using this ReLU activation where we are passing this convolution layer. The output from the Con1 to the ReLU, and then Con2 to again ReLU. And then again for memory efficiency, we are using all this, but behind the screen, PyTorch creates a computational graph when it executes all of this. And yeah, throughout the entire network, we are using this ReLU activation function. Okay. Then I'm just returning the output from fully connected layer, final fully connected layer. I'm not using any kind of this softmax stuff. Okay. Again, we are just building a toy network. So once you define the entire network in kind of using this class approach. Okay, so either you can create the network as, you can think of the network as an object, or you can take a functional approach. So again, it's a choice. you can pick any one. Either you can use a functional stuff or class, but this one is more readable, and also while it's from the deployment perspective, this approach is quite good, okay, or preferable. But if you want to know the entire flow, then functional approach is better. Yeah, you just instantiate the class. Now I have to move the model to GPU, so I am calling this function model to device. Otherwise, it runs when even though I use GPU, if I don't call this, my models make use of the CPU only, not the GPU. So element import. Define it. Now we move it. So you can see the entire model. Just by printing the model, it internally calls model.parameters and displays all these. So the model details. And then now we have an architecture. Then the next step is to, of course, you can see where is the backward pass. Okay, so we define only forward. There is no backward. Backward is automatic in PyTorch. So you have to only define the forward pass. And behind the screen, it creates a computational graph. And then when you call and when you use an optimizer, it actually computes the gradients by doing back propagation and then update the gradients. Okay, so we don't need to, in fact, bother about implementing back propagation from the scratch when we use any of this deep learning framework. Yeah, so to use the different types of optimizers, we use this module optim. And then, of course, from NN, we are using this cross interfilas and all these steps. So only thing is that whatever the optimizer we use, we have to pass this model parameters. So when in PyTorch, parameters means it's not weights. Okay, so it's an entire forward pass. Okay, so that is what we pass. So when we call this, it construct the computational graphs for all the weights. Okay, and let's see, I'm just doing that. And if you want to really see the weights, so you can use something called, it maintains some state dictionary where all the weights are, of course, we cache the intermediate results, then we update the weights. So the best way of storing weights or the parameters in the network is to use dictionary, and especially order dictionary. So you can see that here we have a dictionary with this name on one layer. Okay, we are just calling the weight. Then these are all the initialized weight. Okay, so you can explore all these steps. Even you can cache the intermediate gradients. So like if you want to really visualize how the gradient flows across the CNN, or if you want to do this kind of steps, right? In the second part of the lecture, we discussed so many tricky things to create an art from an image. All these steps can be done by doing some tricks with the gradients. So that we can do with these parameters.
So here we are just doing the forward pass. We are not doing the backward propagation, correct? So we are taking
so far, so far we have just taken the model and then we call this optim. So the moment we call this optimizer, it initializes the parameters. And then it initializes the, so whatever the name you define here, right? So now I defined it as con1, right? So it take all those names and then it creates a weights for each of these layers.
Okay. Based on the input and based on the input image size, and again from the next time it will take the con1 or con2, right? For that, whatever the dimension of the weight, it will automatically initialize only the weight and propagate up to the loss function, correct?
Yeah. Okay. So all those dimensions can be inferred from this configuration. So it with this information, it creates the weight matrices for all the layers. Okay. Then we have to so the next step is simply, now we have defined the loss and then we have initialized the weights, then we have to train it. So the training is quite straightforward. I am just running it for 2 loops. These are all just my variables just to catch the loss. And the only thing is, we move the model to GPU. Again, we have to move the model, the input data and the respective labels to GPU. So I'm doing that here, so that when I run this loop, everything will get executed in the GPU. So this zero gradient, yes, this is again, we have a batch of size 4. So once it forward passes and then compute the gradients by back propagating, for the next set of samples, we have to actually set the gradients to 0. Otherwise, what happens is that it makes use of the gradients for the first set of 4 training samples to the subsequent sets. So it simply keep accumulating the gradients if you don't set gradients to 0. So in order to set the gradients to 0, we have to call this for every iteration or epoch based on the type of optimization algorithm we run.
Okay.
Yeah, of course, there are APIs even which hides all these details. So you can write in many, you can develop a code in 3 different ways. Either you can go to the lower level, still lower level. This is a kind of mid level, and then there are still APIs where you can write the entire stuff in 5 to 6 lines of codes. So then we do this forward backward optimize. So you can see that I'm computing the loss, and the moment I compute the loss dot backward, call this loss dot backward, it actually computes the entire gradients. Okay, and the loss dot backward computes the gradients. It won't update the parameter. So it is like caching in our assignment or in our lecture. Now I have to call this optimizer.step, which actually make use of these gradients to update the parameters. Okay, so again, I'm explicitly putting all this to correlate with the lecture. Okay, and then you compute the loss, all the stuff. So you take max. Then I'm just running this for 2 iterations. I hope it get executed in 2 to 3 seconds. There are 50,000 training samples each. Batch size of 4. Oh, it's going to take some time. So it just has finished 4,000 samples. My data is calling behind.
Yeah, no issue.
Sir, by the way, I hope you're better from yesterday.
Yeah, I'm fine today. So it's I don't know why all of a sudden happens, because I'm watching the computer by 24/7. I don't know. So it's kind of very high irritation. That's why I went to the hospital. Otherwise,
Better use some monitor. I think you are using direct laptop. Okay.
yeah. So yeah, we can see that the loss is consistently getting reduced. Yeah, even for 2 epochs, I think the loss or the accuracy goes to 50%. Yeah, so now the entire training is over. The next step, of course, you can evaluate the model. So it gives all the information. Okay, so I'm just putting the model in the evaluation mode. Okay, so nothing big here. So now from the training mode, I'm moving into the evaluation mode. And then again, I move this test data to GPUs and compute the accuracy on the test data. You can, the same step of process that we followed for training, nothing new here. Yeah, so that's all with this training and testing. You can do this inference. I mean, if you have separate samples, you can predict the labels for your new samples by just calling this. I mean, by forwarding the sample through this entire network. Okay, because you can use this. I just want to give you an idea. So as I mentioned earlier, you can use this transfer learning here. So PyTorch has a lot of neural networks that are trained on different tasks. So AlexNet is the most commonly, and the first one, first convert. That is the sole reason for exploration of DL. And then you can see so many nets in vision module. Okay, so dense net. This is a kind of CNNs are really big, so we can't. It's fitting these models into an embedded devices is quite difficult. So that people has come up with different types of nets and different types of techniques to reduce the size of the model. Denseness is one among them. And you can see all, I think most of the names are familiar to you, except these mobile net, okay, RESTnet, all these things. Okay, so again, there are varieties of RESTnet. How many, what is the depth? Okay, how many layers are there? Based on that, there are 50 layer RESTnet and original 152. So these are all the models you can directly, which means you can load the model. Pre-training means the weights are initialized from, say for example, AlexNet is trained on ImageNet. So we have weights that are well tuned for ImageNet. Suppose if I want to use AlexNet for some other related task, okay, say for example, I want to, there are 1,000 objects. So if I want to train the model on cat and dog, I can do that, right? So instead of initializing the weights from random or randomly initializing the weights, we can start from the weights that are already fine-tuned for ImageNet. So that's what we mean by pre-training or transfer learning. Of course, we didn't talk about this transfer learning stuff anywhere. I don't think. Yeah. So we are going to talk about. So it's a very simple task which you can learn offline or from anywhere. So you can use any net. You can see the architecture of those nets. And even I have I took some images randomly from Google Images or some sites. And then I just passed it through these nets to predict the labels. And you can see that it predicted as jellyfish. Okay. And of course, you can see since these nets are trained on ImageNet, you can see there are a lot of labels. And here, what it almost predicts with a 78% of confidence that it is a jellyfish. But is that a correct one? Do you think this is a jellyfish?
No, sir, it's wrong.
Yeah, so you can use RESTnet and see whether it performs well. So it predicts it's a goldfish with a confidence of 99%. Okay, you can do many things. You can take pre-trained models and you can fine-tune it for your task. So especially this transfer learning is helpful when you do not have enough number of samples to train really big models. You want to make use of big models, but you do not have enough number of samples. Okay, so that's really the model has usually millions of parameters, but you have only some 10,000s or 20,000s of samples, but you want to make use of them. So in such a case, you can make use of these transfer learning techniques. Okay, so I think this is more than enough for the time being.
Yeah. That's enough to start. It's a lot of content.
Yeah, so again, it's just a gist.
Oh, sir, can we get this notebook, sir? So we can.
Yeah, surely. Yeah, I shared the link in the Discord. So
Yeah, sure. Yeah.
Okay, sir.
So that we cannot forget the syntax or how to write. And can you also tell some good site for the syntax, or we can get from the collab directly? Some good site.
There are many. So okay, I consolidate.
Which
the
one you
that I
prefer?
have used.
Easy.
Yeah, actually, there is okay. I go through. I have saved some of them. I make consolidate all those sites and put it as a post in the discourse.
It looks like TensorFlow. It looks like TensorFlow only. They're using the sequentials. TensorFlow. But some commands are matching, like the way you are using this con2d max tool.
Yeah. So I
similar
mean,
to,
if you are familiar with one framework, then you can easily. So familiar in the sense, if you know how the framework is constructed and how the modules are separated. Okay. Essentially, so if I remember it correctly, so long ago, right, way back in 2014 and 15, when people started building this TensorFlow and PyTorch, and then there comes the Keras as well. So they have different approach of computing the gradients. So TensorFlow builds something called a static computational graph, and then when you run it computes the gradients. But PyTorch relies on dynamic computational graph. So those are all the differences between these. But once you understand the, this, if you understand the architecture and the entire operation involved uh, for the specific architecture, say when I say architecture, when you understand CNN, then most of the CNN architectures use the same components in it's a modular, so you can build in any way you want. So all the frameworks use these standard names. So if PyTorch use con2d, most probably TensorFlow also use con2d, and Keras also use con2d. And they also have these very high level IPAs where you can put nn.sequential and then put all these stuffs in a single line of code, then it computes everything. So whatever I have, so if there is a need, say you are familiar with PyTorch, but if there is a need that you have to use Keras or TensorFlow for any purpose, right? Then you can, it's not a kind of difficult, the transition is not going to be that much difficult. So it is going to be quite easier.
yeah, okay, thank you. Yeah.
Okay, so now let's move on to Himanshu. Yeah, Himanshu, what's your doubt? So it is with respect to vectorial representation of codes, right?
Yes, sir.
So is this with respect to the slide content or in general doubt?
Okay, yeah, like some of them with respect to slides and some of them in general.
Okay, so let's go one at a time. Can you remind me of the first thing? So which you asked about cosine similarity something.
Yeah.
Okay, so shall we discuss about that first? Okay. Okay, now you can ask your question once again. So I try to understand the question.
Right. So like what happens, like how to calculate cosine similarity, like mathematically, one, and two, what does cosine similarity represents?
So it's a measure, right? So first thing, we need some. Where can I control? Okay, so all these are just. I hope you are able to read this, right?
Yes.
Whatever I write on the whiteboard.
Yes, sir.
Okay. So we need some measure. So I have what I have is I have two vectors. Okay. Let's say maybe x comma y. And these two vectors for if in this lecture, these two vectors represent the words. Okay, so we encoded words or we embedded words into a vector. So what we really want is I want to measure something. So this something is how these words are related. This relationship can be defined in multiple ways. Okay, how two words are related. Essentially, I want to compute something called as distance. Okay, so I am measuring this relation using a distance measure. Okay, so if the distance is less, I'm just telling these words are closely related. If the distance is very big, then I say these are not closely related. So to measure this, the one obvious thing is we can use, because x and y are just vectors, we can represent these vectors in a coordinate system, right? And when you represent this, it will take some the position of the vectors we associate a position with these vectors, and then x may be here and say y may be here or anywhere. Okay, so again, there may be another word z that is here. Okay, so now we are in a coordinate system. We represented the vectors as a point in the coordinate system or as a vector in a coordinate system. Now we want to compute the distance. Okay, and when I compute this distance, I want to preserve something that is natural in the real world. Okay, say for example, if x is a vector for the word men, okay, and z is a vector for the word king, okay, and y is a vector for the word maybe for women, okay, and I really want to when I measure the distance between men, this x and z, I want it to be closer than x and y. Okay, so that is my wish list. Okay, so for that we can make use of either Euclidean distance measure or the cosine similarity between the two. So now the question is, what do you mean? What is cosine similarity? Okay, so the cosine similarity is most commonly used one, but before using it, we have to think whether it is suitable for our task or not. So cosine similarity is actually based on the angle. Okay, so we have this cos theta. Okay, and if I have two vectors, okay, x dot y modulus of x modulus of y. Okay, so of course you can take this, you can normalize all this stuff. So if I'm not wrong, I think this is the formula, whether theta is equal to cos inverse of all this or theta, and these two are equivalent, I guess. Okay, because the range is going to be in plus or minus 1. So yes, when you compute this, right, so you get answer in the range of -1 to +1, and of course it is very difficult to interpret when I get this -1 or any negative answer. We say they are negatively related. Okay, so we can argue whether men and women are exact opposite, but we don't know, so it's very difficult, right? In what sense they are exact opposite. So interpreting these numbers is especially when we have these negative numbers is quite difficult. It may depend on the application. Okay, but when we restrict this number between 0 to 1, okay, because now what we have been talking about is this distance, and when we say distance, the distance is always positive, so it should be non-negative, and we restrict the range between 0 to 1. Okay, so there is one problem associated with this cosine similarity. So especially this dot product is the main key takeaway. Okay, so when you compute a dot product between two vectors, we are actually computing this cosine similarity between these two vectors, and then this is just an additional normalization part. Okay, and what do you think, what will be the problem with this approach if I use cosine similarity instead of say using this Euclidean distance?
Negative and positive angles that are closer will be marked as closer, or when something gets closer to one word, it will also get closer to the context.
Yeah, that is one thing. This negative thing is one, but there is one more problem associated with it. The thing is that, of course, we do this set of normalization to eliminate that problem, but I'm just want to highlight this here. Okay, so now the problem that we might encounter is that I may have a word. Okay, so in fact I'm just kind of measuring the angle between these two also, because I'm using this cos theta. So somehow I'm using this theta as a measure of distance. Okay, so I can have another vector, okay, that might also lie in the same direction. Okay, and another vector that also lie in the same direction. Okay, it is possible. So if I use Euclidean distance, say for example, if I take these 2 points, okay, so in the same angle, in the same direction, Euclidean somehow gives me a different measure for the vectors located, though they are in the same direction, but since the Euclidean distance might change if I move in the same direction, like it's a kind of from the origin I have here. So it's a kind of measuring the distance between those 2 points and then these 2 points. Okay. So Euclidean distance distinguishes these two, but the cosine similarity won't. Okay. And again, we have to decide whether we have to cosine similarity is more helpful for this specific problem, or Euclidean distance is more helpful for this specific problem. This is a design choice. Okay, and if I remember correctly, there are more than 3 to 4 distance measures that those are kind of classical distance measures that we use in natural language processing. Okay, and also I am not sure and I am not familiar with many of them. They are very task specific as well. But as far as this cosine similarity is concerned, this is one of the problem with cosine similarity. Okay, so now I hope now you get an idea of why we use cosine similarity, and this becomes a natural choice, especially when we do this SVD decomposition and when we take this x into x transpose, right? We have this co-occurrence matrix, and then we do this SVD decomposition, and we do this first approximation by taking this x into x transpose. So where we in fact compute a dot product between this vector in x, sorry, this row vector and the column vector, we have this natural interpretation of cosine similarity. Okay, so that's the reason why we go for cosine similarity, because it gives us some natural interpretation. Okay, so
Okay.
that's all what I know about this cosine similarity.
Okay. Okay. Sir, the two vectors that are overlapping each other, but they are different in magnitudes.
Yeah, by the way, we are normalizing it.
Yeah, so in that sense, then those two vectors are exactly equal, like.
Yes.
So, like in terms of cosine similarity, does they mean anything? Like.
Yeah, so if they are kind of pointing in the same direction with the same magnitude, so it implies that the meaning, I mean, they must be very, very close to each other. It's a kind of, I don't know, maybe the example, say if dog and cat are pointing in the same direction, the same magnitude, then the distance is obviously 0. Even the angle between them is 0, right? So how do you infer this? So it says it's 0. So the inference, we can say both are animal, right? So again, I'm taking this as yes, they are both animals. So in that sense, they are same. So no distance separation between them. So it's everything boils down to this interpretation, and we don't know whether that is a right interpretation or not, but we try to make sense of these relations. In fact, I thought of giving you this, giving you a programming exercise to decompose the co-occurrence matrix and computing the first order approximation. Sorry, in the sense rank 1 approximation of co-occurrence, and then project it down to 2D and then try to visualize how the words are correlated. But I thought it's way too much cramming so much material onto you. So I just, didn't give you
Okay.
as an assignment.
Okay. Maybe, sir, if you want, you can post that in Discord.
Okay, sure. So anyone wants,
Right.
and
Yeah, I definitely want that. I think other people would be interested. But sir, you talked about doing SVD, right? So when we do an SVD of correlation matrix, specifically the one that we constructed using PPMI, right?
yes, yes,
So the SVD will give negative values, right?
yeah, sure. Sweetie, if you do this kind of approximation, you might encounter negative values.
So now, sir, since we specifically eradicated those negative values with the PPMI,
Yes,
like what does this negative value means?
yeah, that's the difficulty. So it's very, I mean, interpreting the negative values is not quite straightforward. It might, we first it is problem dependent. So what sort of vocabulary we have used, and what is the nature of documents or text we are dealing with, it might keep changing. Uh,
Right.
that
Sir, just to add, and then you can give an explanation. Why don't we also get rid of the negative value from SVD, like the way we get rid using PPMI?
mm, so which means when you decompose, so first thing, we have some properties with co-occurrence matrix. So one thing is, if I'm not wrong, so it is going to be symmetrical. Okay.
Yeah.
So when you decompose a symmetrical matrix using SVD decomposition, so I'm not able to recall things at this moment. We must have some benefits, but I'm not sure whether it eliminates the negative numbers.
No, sir, we like eliminate those negative numbers using PPMI, right? Positive PMI.
Hmm. No,
Uh,
PPMA has a different interpretation, right? So the main objective of using PPMA is to, some words are most frequent in any document, like the articles, propositions, right? So we don't want them to dominate during the, uh, you know, while constructing the word representation for a set of words in vocabulary. So only to eliminate them, we go for this PPMI and PMA. So it's a kind of, again, um, from the mutual information. So again, it's kind of entropy is coming into picture. And then we see their probability of occurrence, the joint probability of occurrence. So if I have word X and then word Y, then I'm just see how often they occur in the entire document or text, and then how often they independently occur, right? So this is how often they together occur, X comma Y. This is how often they occur independently. Okay, then I am trying to normalize them. So instead of just putting a cap, just say if it is beyond 100, always keep 100. I mean, instead of doing this straight thresholding, which may not be suitable, so we measure this kind of joint probability and then marginals. Then we try to come up with some better number instead of having this 100. So that's the sole reason that we go for this PMI and PPMI. And since
Sir, but PPMI stands for positive PMI, right?
yes,
So does that not mean what was explained in the lecture is we take zero and then maximum of zero and then the number like a ReLU function.
yeah, let me share the, maybe, as I'm not able to recall that in a moment. Yeah, so I remember that we are taking a maximum of that.
Yeah, so either that
Uh,
will be then PMI zero. Either like I am confusing or you are confusing something like that. So yeah, here. So
Yeah.
in this, either we take the positive number if the whole PMI is positive, otherwise we take it as 0. So the
Yeah,
last time.
yeah, so the PPMI, yeah, we are looking at PMI. So if PMI is greater than 0, we keep it as positive, of course. So yeah, it's a kind of max function. Here,
Yeah.
what we do, so when
Count,
do we have this
sir.
PMI positive? If my count W comma C is greater than 0, right?
Right.
So if it is greater than 0, then my PMI will be positive. What is how it get related? And I am just curious when it can become negative. I don't think it. Yeah, so we are taking a log of it, right?
Yeah. So like below 1, when x is less than 1.
Yeah. So first thing, so I am taking PMI of W is count of W comma is. So I think Mitesh had discussed about this in the lecture, even though I'm not able
Yeah.
to. Since we are using this log and when log becomes negative, so if my this range, so I'm just these two are probabilities. So if they are probabilities, then the numerator is always between 0 to 1 and the denominator is always between 0 to 1. So the ratio, I don't know, it's a conditional probability. So together they should be 0 to 1. It cannot be greater than 1. So if log is in the range of 0 to 1, then we get, what is log of 0? It's negative infinite, right?
Yeah.
Log of 1 is 0. So all the numbers are going to be minus infinity to 0. Okay. Okay, so now, so that's the reason why they go for this one. They force it to be positive.
Yeah. So sir, but like in the last one, we force the whole PMI to be positive, right?
Yeah.
And then after, like, my question was after that, when we do like we use PPMI for the specific reason that there is a negative correlation between the words do not make sense.
Yeah. That's the sole reason. And that is also
Yeah.
one of the reasons. Yeah.
Right. So then when we perform an SVD on that matrix, it will give us negative values, right? So like, how do we make sense of that one? And like, why don't we just eliminate 0 from that also?
No,
Like, if we
when we
cannot
do
make
this,
sense, then
yeah. So I understand your question. So while we compute SVD, right? So it actually diagonalizes the matrix into 3 parts. So what you are actually saying is, hey, this is U and sigma, and then say it's U transpose, something like this. So what you are saying is that either in my U or sigma, since it is symmetric, my eigenvalues, I think all of them are going to be positive. Maybe I can get some negative values here, right? Either in U or in V. So you are talking about eliminating the negative valued elements from U and V.
yeah. So that
Because
after we perform the K rank SVD, we should not get 0 value negative values.
so I am computing SVD on this PPMI matrix, okay, PPMI matrix, where my PPMI itself contains all our positive valued elements, right?
Yes.
Then I do this decomposition, and possibly I get some negative values. But when I do this approximation, right?
Right.
So when you do this approximation, I don't think, of course, unless we work out, we can't sure. I am not sure. We don't think the resulting matrix will contain any negative numbers. After taking, say,
Okay.
for example, take this row and then scale and then do this rank 1 approximation or rank 2. So when we do this, I don't think there will be negative numbers. maybe independently we can have it, right? So if you look at the elements of V and D, we may have some negative values. But when we reconstruct PPMI or when we do rank K approximation, that rank K approximation may not have negative numbers. So that is my guess now, but we have to work out and see whether
Okay.
will
So
the
like, okay, so I did ask you about this, whether or not. So you said yes, which is why I proceeded with the question.
okay, maybe I might have
Okay, it's okay then.
Okay.
Yeah, it's okay, sir. So why do we use cross entropy loss? Why don't we use like other loss that we use throughout?
For which one you are asking this? Why do we
For
use
bagging, forward bagging.
forward? Can you say forward bagging?
So for
I don't know whether I'm again.
no, sir. For continuous bag of words algo, we use cross entropy loss, right?
Yes, yes. Yeah, give me a second. I may go to that slide because
So we
yeah.
use this because the resulting value should be a probability.
Yeah, that is
So
the main reason.
okay.
Yeah, because first thing, of course, there are two branches of machine learning, right? So one is kind of probabilistic models. They build the probabilistic model, so everything is in terms of probability. The other one is, of course, these neural network models, but we would like to have this probabilistic interpretation, right? Because once we bring in this probabilistic interpretation, then we can make sense of the result. So that's the sole reason why we use this, of course, softmax and then cross entropy loss, because now this is kind of classification problem. So cross entropy loss is the most suitable one. So that is the same reason that we discussed for when we discussed in lecture 4, I guess.
Sir, in the hierarchical softmax,
Okay.
we mentioned about making the binary tree, right, at the end step.
Yes, this one, right? Yeah.
So I cannot see it. I am still seeing the whiteboard.
Sorry. So this is, I think, I'm not able to share the entire screen. Is that possible? Okay, here it is. I think this is better now.
So, sir, like in the ending, sir mentioned about some complications why we do not like when we randomly create that binary tree.
Yeah.
But I don't know, like the lecture was missing or something. The reason was not mentioned throughout the lecture. Like, can you say the complications that we encounter when we randomly create the binary tree?
Yeah. So of course, first thing I have to acknowledge is that when I started digging deep into this hierarchical softmax, okay, so of course it is being used in all language models, especially when we have these thousands and thousands of output classes, and we end up using the approximation of softmax, either negative sampling or hierarchical softmax. Okay, so I'm not totally convinced about this, this entire concept about hierarchical softmax. So one thing that I learned and also kind of convinced is that when we use hierarchical softmax, when we randomly create a binary tree, right? I'm just telling I'm convinced, so I'm telling my answer. But if you are not convinced, then of course I will be glad to hear from you after you found the answer. Okay. Yeah. So what we have in the vocabulary, right? Maybe 10,000 words, say for example. Okay. And when I say one word has occurred, and by the way, so when before moving into that, I can count the words in the given document or in the given entire Wikipedia, and then I can plot the distribution of the occurrence of words in the entire Wikipedia article. Then I know that some words are most frequently occurring. Okay, this is without assuming anything. Some words, say for example, maybe the word the is most frequently occurring one, a, an, all most frequently occurring one. So the thing is, some words are most frequently occurring. This is not conditioned on any other word, so it's an independent. So when we look all these words independently, the is might be the most commonly occurring one. But when we put this conditional probability, then this keep on changing. So, but one thing is sure. What is so sure is that okay. Say for example, again we take the same thing. Say for example, maybe SAT. Okay. So when I give this word SAT, SAT, then I may ask you what will be the next word. Okay. So most probably, even though I have rest of 9,999 words, these are all possible. Okay. But I'm sure that only a subset of them are going to be make sense, right? So maybe the next word could be set, of course, sat on, but let's say it's a chair or desk, or maybe sat on tree, even it is possible, okay, or boat, something like this. Okay, only these words are going to be are highly likely words, and those highly likely words are going to be very, very less than, and we are intuitively know that it is very, very, it is going to be, say for example, even I put 1,000 the likely words. Okay, it is much, much less than the entire words in the vocabulary. Okay, so the idea is, since we know that some words are most frequently occurring than other words, I need not to go through the entire all the words in the vocabulary. So by making this observation, what we can do is that, remember in hierarchical softmax, the thing that we want to achieve. Okay, so I'm just putting some tree diagram. Given the word sat, okay, and the most probable word may be chair. Okay, I'm just again an example. So I want to reach them as quickly as possible. Okay, so I want the distance. Okay, so the number of edges that I reach from sat to chair should be less. Then I reach the word sat to, say for example, maybe a very high depth. What is the improbable word? Maybe will. Okay, it is highly improbable. So for this word, I want the number of paths, or the length of the path to be bigger than, say for example, I want this to be at level 10 in binary tree world, let's say, and I want this to be found at, say for example, level 3. Okay, because these are most likely words. Okay, so one thing people commonly do is that there is an algorithm called as Huffman coding. Okay, that is kind of taken directly from again based on entropy. Okay, so what Huffman coding does is that it also comes up with the of course there is an approach to build the Huffman tree, but the idea is that if there are in my vocabulary, if there are more how do I put that, for most frequently occurring word. Okay, so I'm just naively say this for most, okay, in Huffman coding we call this as something like this, for most frequently occurring word. you assign the less code. Okay, say for example, if I assign if I do some binary code to all the words in the dictionary. Okay, so the binary code simply implies taking left or right. So we use this 0 1 1 0, right, to take whether I take a left path or right path. Say I am assigning 0 1 to sat, and after using this Huffman tree approach, 0 1 will be assigned to this word sat, and then we'll have a coding assignment, binary code assignment. Okay, or the will be encoded as 0 0 1 0 1 0 1, whatever the, but I know for sure that the length of the binary code assigned to the word will be bigger or lengthier than the word sat, because I'm assuming sat is occurring more frequently. So it requires only a kind of course, this is again based on entropy. So you assign this kind of binary code assignment to all the words in the vocabulary, and then you measure the entropy for these words. Okay, then it turns out that using Huffman coding is best way of doing that. Okay, best way of doing that. Okay, so I hope you are able to get what I am trying to convey. So if my word is sat, then I want all the next probable word to be closer to sat, in the sense the path to reach them must be closer. So why am I imposing this condition? Okay, so once I reach this leaf node, then I update only these parameters. Okay, parameters encountered here. I don't need to update all the parameters that are connected to the softmax layer, because that is unnecessary. Sat is, it is highly unlikely that you encounter the word sat and will together. Okay, of course we are just conditioning on a single word, but when you condition it on a window of size 4 or 5, then most of the words are highly unlikely to associated with some other words. So I don't really want to update the parameters associated with these. Okay, I really want to update the parameters only to a subset of words that has a high probability of occurring with this particular word. Okay, so that is why Huffman code is, I think this is one of the approach to build this binary tree instead of doing randomly. So if you do randomly, maybe my chair will go here, right? The word chair will be in a higher depth and assigned with some really big binary number, which means I update all the nodes that I encounter while I traversing the path to reach this node. So that is unnecessary. Okay, I may update the word will. Okay, the parameter associated with the word will, which is highly unlikely, but I'm still updating it because it is, it is in the path from sat to chair. So that is why doing this random building of binary tree is not an efficient way. People has, so of course, I don't think there are proofs, right? Using Huffman coding is the efficient way. People has experimented with different way of building binary trees. It seems that doing this randomly is not at all working, and they come up with some justifications that make sense. So this is the one that I have.
Sure, but we as written on the right side of that slide, we use maximum likelihood, right? We use these probabilities to get to the leaf node, right? In this condition, all the words will be at log e height.
Yes, you mean log?
Log e, right? The height of the binary tree is log e, right?
Yeah.
So all the
Yes.
words will be at exact log e height, right?
Yeah, that's also makes sense. So which means, um,
all the words will be at the same length. So Huffman encoding won't help us.
No, Huffman, actually, I don't know why. I mean, Huffman is actually not a balanced tree, by the way. So here we are talking about balanced tree, right? So if you use Huffman encoding, then tree will not be, I mean, it cannot be balanced because of this assignment of code to each word. So that is one thing that we have to ponder about. I don't know whether in reality uh, they use this balanced tree or not in the real world.
Okay.
Because in
Okay.
balanced tree, as you climb, or I have to look what is the advantages. So we have to actually look at the nodes that we encounter while we traverse from the root node to the leaf node. Whether those nodes are, kind of, because we are going to update the parameters of those nodes, and we have to check whether those nodes are really associated with that particular word.
Okay. Sir, but like based on the example that sir gave us, like the only thing that matters like here is the path should be unique, right? So based on the direction, either it will be either 1 or 0.
Yeah.
So like we can not do that in Huffman encoding as far as I think so, because as you told, since it's not stable,
So
the
Huffman,
path length will.
yeah, the path is unique, but the length of the path is not going to be, it's not going to be same for all the nodes.
Yeah, so like is that a problem?
Which problem?
Since the path length will not be unique, can we like, okay, so that should not be a problem because we are just having the maximum law likelihood, right?
So I mean, are there any mentioning about that in this slide, or he just talks about that?
So he talks
Yeah.
about that exactly like last minute or last 2 minutes.
Okay. I think that's the end of
So
the
see here,
lecture.
sir, at the last, like if you just go back, so how like the last two points.
No, I'm quite of disagree with that. So I have seen papers where this. I mean, even I think in 2005 or in 2008, Benjo et al. Actually proposed this hierarchical kind of modified hierarchical softmax, where they actually claim that this random arrangement of words is not quite efficient.
Okay.
So I actually direct you to those papers, whoever proposed it first, right? And
Yeah.
also related papers who carried out extensive experiments to validate these claims. Because
Okay.
I don't know, when you put a random, so, and of course, most of the time this path itself is learned. It's not kind of using this fixed Huffman approach also, because Huffman is based on this distribution of
Sorry, sir,
words.
just a second. But as far as I can remember, sir mentioned that when we go to actually calculate the likelihood, the maximum likelihood, the binary tree is fixed at that point.
Which slide is that?
Okay, like I think it's verbal or it might be in this slide. I do not know that. But as far as I can remember, sir mentions that when we actually go to calculate this maximum likelihood, the tree is fixed. Like the tree will not change.
Yeah, so I think it is after kind of training or after building this tree, right? So he didn't talk about how to build this tree. It is like you take that for granted. So the tree is given to you after doing some kind of magic. You are given with the tree. Now you can make use of it. Then that's fine. But how do you build the tree? So that's where this Huffman coding and learning the tree itself, everything jump into this picture. But I would like to highlight that we, of course, digging details into this are really helpful as for us to learn in depth. But the key takeaway that we should not forget about why we go for this hierarchical softmax is this. Okay, so all the words are not equally likely. So when one word occur, other words are highly likely than the rest of the words in the vocabulary. So while we update the parameters, so the core problem that we encounter with using softmax is for each iteration, I update the parameters of all the parameters in the softmax layer, which is not necessary and also expensive. Okay, so doing that is quite good because even though it is unrelated, it get some gradient value, maybe 0.001, but it is quite expensive. So that's why we exploit these, dependency between the words, conditional dependency. So once we recognize only these set of words are co-occurring, whenever this particular word occur, then the next word and the previous word, these are all the set of words that co-occur, then updating those parameter itself is more than enough to get a decent performance. So that is the one of the key takeaway about this entire topic: negative sampling, hierarchical, softmax, contrastive, I don't know, examples or something. So that's a core thing that we have.
Estimation.
Yeah.
So the word was estimation. Also,
Contrast
like that, that lecture was missing in the portal. So like, was that intentional or?
No, the contrastive estimation, I think we didn't talk about that much, okay, because we don't know that much. Even I know only those two words about that contrastive estimation, okay. That's why we actually didn't talk about any of this in detail, okay. So because we really want you to understand these things are exist. So when you really, make use of or if these things are really needed for you to implement something, then you can dig deeper, okay. Otherwise it's a kind of already we are pushing a lot of contents on each topics, and also we have kind of cut short of so many contents. Even we didn't cover about different initialization techniques, normalization techniques, which we are initially planned. But because of these, instead of cramming so much material on students, okay, when they learn everything for the first time, we are just giving the gist of everything. So that's the reason. And one more reason is, even if you ask me what is contrastive estimation, give me in detail, I don't know. I know about negative sampling and hierarchical softmax because they are most commonly used. Contrastive is exist and more other techniques are there, but it's a kind of research level. Okay, so unless we do some sort of research along the direction, in my personal opinion, digging the details of it and covering it in the lecture is an kind of um, not required thing.
Okay. Sir, also, can you just confirm the parameters that we update in the bag of words model? So that is the whole W context, the whole W words matrix, and a single row of, and a single column of W context, right?
So the parameter that we update in general, you are asking for the entire architecture, right? So it's an entire network.
Yeah.
So W context, no. So W context is the matrix, the parameter matrix. So if we don't use any of these approximation techniques, we actually update all the parameters in W context and all the parameters in W word. Because even though you take only two words, okay, it doesn't mean these words have no relation with any other words, because it is like we are predicting, right? So I just would like to know why you think so. Why you think only updating that parameter is sufficient? In this slide, we are just showing you how to update a single parameter. But in fact, we are updating all the parameters in W context and W word.
Because sir, I think sir mentioned something like this, that since it will be a one-out vector, only one column will be there. when we multiply
Yeah,
in the exponent.
yeah, that's the
Uh,
gradient from the output layer, right? So only one, I mean, since it's one hot vector, we have only one word, but the prediction is for all the words, right? In my true label, I have only one for one word, but my prediction is for all the words. Then while I do this backprop, I pass this gradient to the in softmax. When the gradient passes through the softmax, it actually computes the gradients for all the words. Then it again passes down to the hidden layer where all the parameters get updated. So that is the bottleneck for us, because the softmax layer, the number of classes are going to be 10,000. And say, for example, if my hidden layer contains, say, for example, 100 neurons, but the output layer contains 10,000 neurons, then the number of parameters are going to be 10,000 into 100, which is 1 lakh, 10 lakh, kind of 1 million parameter. So do I need to update 1 million parameters? It's quite a difficult thing. Okay, doing this through for each and every word, we update 1 million parameters only in the output layer. Okay, so that seems to be quite extensive computation because of this exponential stuff. Because softmax use exponential, then exponential has a problem because exponential quickly explodes, and there are a lot of issues with exponential thing. You can actually search it. Why? What are all the numerical issues with computing softmax? So to avoid that, we go for the approximation of softmax. So that is the reason.
right, sir. But when we use SVD, right, we can limit the context based on some k.
Yeah, that is approximation. But when you do this reconstruction, then you end up with the same dimension, right? If my
Okay.
original
No, so I
dimension,
was confused between that one or I thought since we are only using one to predict it, so we will update one.
yeah. So that is in fact just to show you how to update parameter for a single word. Mitesh had used particular row and column, but in fact, in reality, all the parameters in W context and W word gets updated.
Okay, so like that's it from my side for today. Next week I will be back with more questions.
Okay, thanks, Himanshu. And Aditya, you can go ahead. You have been waiting for a long, listening patiently.
Sir, I have just a little question. In the lecture, when sir was plotting the graph for the max function.
Which lecture? So it's for CNN or?
Oh no, sir. In I think in week 7, when sir was plotting graph for max function, max minus 0.5x, comma 0.5x. So I didn't understand the plotting, sir.
So you mean the max of neuron, right?
Yeah, just the max of two function. How to plot the graph?
Okay. So yeah, so that is related to max of neuron, I guess. But anyhow, so it is like you have this max
Minus 0.5x
minus 0.5x.
and then 0.5x.
Okay. So plotting this is, say, first we take 0.5x, right?
Okay.
So it is going to be positive slope. So you have something like this.
Okay.
This 0.5x.
Yes.
Then for minus 0.5x, you will have something like this, right?
Yes.
Negative slope. Then taking max out of means, so now you are looking at this half. Okay, so you break down this real number into two halves. So I mean, you go over for each point, right? So at this point, I have two numbers, by the way, which means when x is equal to 1, I have
Yeah.
minus
So,
0.5 comma plus 0.5, right?
yeah.
When x equal to 1, which means I'm evaluating the max function at x equal to 1. So I have two numbers. One is minus 0.5, another one is plus 1.5, and max is this one. So you can repeat this process and you can see that, this is a positive side. So this is the negative side. So
Yeah.
it gets eliminated when I pass through this max function. I'm passing 0.5x and minus 0.5x. And now x is contained in the range of 0, infinite. Okay. So there I have only 0.5x for all values of x.
Yes, sir.
So for x contained in minus infinite, 0,
Yeah.
I have which one? Because I'm multiplying x negative number, so this becomes positive and this becomes negative for the
Yes.
negative half. So it will remain, this will get,
Yes.
now you get this kind of,
Yes, sir. It is easy. It is easy one.
yeah.
Yes,
Of
sir.
course, when we have more than two arguments, okay,
Yes,
then by the way, for a specific number we can evaluate, but plotting the graph, it's a kind of what is that, piecewise linear approximation of some function.
Sir, can you upload the answers for week, like graded assignment answers for week 4, 5, 6, 7?
Yeah, sure. I think I uploaded it for week 4. On 5, 6, I uploaded Himanshu maybe before quiz, because I'm currently working on 2 more tasks which are quite urgent. Then after I finish it, I upload it. I hope
Sir,
to
about
do that before quiz.
transformers, right? You're talking about transformers.
Yeah. So again, we don't think we are able to cover transformer fully. We try to cover it. I mean, we will give you of course, we are planning to give you about the transformer architecture, the components of the transformer architecture, not the training aspect. So let's see how it turns out.
So in which week we will see transformers?
Week 11.
And what is the contents for next week?
It's RNN. So that's another major module in DEL. So it's RNN and then it's different versions. Then we also talk about attention mechanism. So you can see it here. And it is also going to be quite dense. But anyhow, this one is easier. Then when you encounter this LSTM, all this, it becomes quite complicated, but comprehensible. And you will have week 11, transformer moves to week 11, and then week 12 is kind of a live class with professor. We're planning to give you a live class where you can interact with the professor, and also we talk about some concepts in transformers. And we are actually thought of covering this bird, all these stuffs, but maybe we will release the material. You can go through it for your learning, not part of the course, but for your learning.
Okay.
Yes,
thank
sir.
you, sir.
Thank you, sir.
Okay. Thanks a lot for joining. I think, when is your quiz? It's November 20, right? Yeah. So
Yes.
next we have a revision session on coming Monday. So
Okay, sir.
the revision, I am not going to exhaustively again talk about all these stuffs. So you go through the week 5, 6, 7, 8.
Yes,
5,
sir.
6, 7, 8 lectures, and if you have any specific doubts, get it clarified there. Okay.
Okay, sir. Definitely.
Yeah. Okay. Thanks a lot, Himanshu and Aritya.
Okay. Thank you, sir.
Bye. Yeah.
Bye.